Hello, this is Mrs. Johnson. This is MAT221. This is Calculus 1. We're in section 4.4 that talks about graphing using calculus. What we're going to do here is we're actually going to use the shortcuts and the ideas that we developed in Unit 2 having to do with the derivative and how it's related to the first and second derivative and how it's related to the original function. And then combine that with what we just learned in section 4.3, which was the first and second derivative test and the concavity test. So let's look at what I did here is I went into some worksheets that we have in Unit 4 that talks about section 4.4 that's talking about graphing. So this particular worksheet says, let's do the interpretation of the derivative. This was sheet A. There's also a sheet B that's actually attached to this. So what I'm going to do is I'm going to go through this one, and then I would encourage you to go back and do interpreting the derivative worksheet B by yourself using what you learned from this one. So this says the graph below represents the rate of change of a function, f of x with respect to x. Note that the graph is the derivative of the function. So we're looking at the derivative of f. And the only thing we're told about the original function is that the original function has a starting point at negative 3.5 of negative 2. So that's the only thing we know about f of x, other than that this is its derivative, the derivative of f of x. So knowing that, it's asking us on what intervals of x from negative 3.5, which is this endpoint right here, you can see this endpoint, to 4.4, which is this endpoint right here. On what intervals is f of x increasing? Now notice they're not asking us about this graph, they're asking us about the graph that we can't see. But the graph of f of x has a derivative that looks like this graph that we see in front of us. We know from our interpretations of the derivative that a function will increase when its derivative is positive. So what I'm looking for here is, where is the derivative curve have positive outputs? And you notice that the derivative curve will have positive outputs from negative 3.5 to negative 1, because the output of the derivative will be positive values above the x-axis. And then again from 0 to about 1.5, the derivative will have outputs that are positive. And then again from 4 to 4.4. Notice the derivative lies above the x-axis there. So my answer to this first question, f of x is increasing whenever the derivative is positive, and the derivative is positive on the domain intervals from negative 3.5 to negative 1, and then again from 0 to 1.5, and then again from 4 to 4.4. Now these can get tricky because we have to be careful what we're looking at. Remember, we're looking at the derivative of the function and answering questions about f of x, the function we can't see. The second part of this question says, on what intervals or intervals of x from negative 3.5 to 4.4 is the original function decreasing? Well, here we're thinking just the opposite of what we just thought. The function f of x, we know, will decrease when the derivative function is negative. In other words, when the derivative function has negative values. The derivative would have negative values where the derivative lies below the x-axis, and that would be from negative 1 to 0, and then from about 1.5 to 4. So again, here's our answer. F of x is decreasing whenever the derivative curve is negative, and this is occurring on those intervals. Next, it's asking us on what intervals of x on this given interval is f of x concave up. Notice again, they're not asking us about the graph we're looking at. They're asking about the graph we can't see, f of x, whose derivative is shown here. Now let's go back and remember, what do we know about concavity? We know that when the second derivative is positive, the original curve will be concave up, and the derivative curve will be increasing on this interval. So we're looking at the derivative curve, so we're going to use that notion here that when the derivative curve is increasing, that is where the original function will be concave up. So let's look, where's the derivative increasing? The derivative is increasing from 3.5 to about 2.8, negative 2.8. And then from about negative 0.5 to about, I don't know, positive 0.9. And then again here from about, I don't know, 3.2 to the endpoint. So we say f of x is concave up whenever f prime is increasing. That's the graph we're looking at. And this will occur in those domain intervals from negative 3.5 to negative 2.7. I said 2.75. From negative 0.5 to positive about 0.9. And then again from about 3.2 to about 4.4, as long as we're in the ballpark. Part D says, at what values of x approximately does f of x have points of inflection? Now remember, possible points of inflection occur when the second derivative is equal to 0 or undefined. And how do we determine that from the first derivative? Well, we say, well, what would be where the second derivative would be equal 0? Well, that is where we would find horizontal tangent lines of the derivative curve. So we're going to look at the mins and maxes of the derivative curve. Also remember that the second derivative, when the second derivative changes sign, those give us points of inflection. And remember, the second derivative will change sign when the first derivative changes direction or changes from increasing to decreasing. So we're saying, okay, look, the second derivative will be positive, then 0, then negative. Notice the second derivative will change sign at about negative 2.75 or so, 2.8 or so. Here again, the second derivative will change sign from being negative to positive, because remember, the second derivative is the derivative of the derivative. The second derivative will change sign from being positive to negative, so here will be another point of inflection. And then here, where the second derivative changes from negative to positive at about 3.2. Next, it asks me in part E, what x values, where are the x values of f of x, that f of x would have local minimums and maximum values. Now this we just did in section 4.3, but we're not looking at f, we're looking at the derivative of f. Remember, by the first derivative test says where we have critical points where the first derivative is equal to 0 or undefined. These are possible maximums and minimums. So let's look. Here we go. Here's one. The derivative is equal to 0. 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 Here are the critical points of f, where the derivative is equal to 0, and the derivative is always defined. So let's look at each point here. Well, let's see. We're going to start at an endpoint. We started at 3.5, negative 2. And then the derivative is above the x-axis, telling me that the original curve is actually rising. So this endpoint right here is the beginning part of the curve, and then the curve f of x rises. So this would actually be a local minimum value. What about this one? This critical point, the derivative changes from a positive value before the critical point and then a negative value after the critical point. Therefore, we have changing from negative to positive, right? We have a local maximum. Here we have a critical point, but the critical point is not changing from positive to negative, right? The derivative is changing from a negative derivative to a 0 derivative to a positive derivative, because remember, we're looking at the derivative curve. This particular critical point here at positive 1.5, the derivative is positive above it, then 0, then negative below it. Remember, we're looking at the derivative, so we can see that the derivative of f changes sign there from positive to 0 to negative at 1.5. Again, at this critical point, the derivative changes from, I have a negative derivative, then a 0 derivative, then a positive derivative, so that's going to be a min. But then this endpoint over here, the derivative is positive until it reaches that endpoint, which means the curve is increasing until it reaches that endpoint. not this curve, but the original curve, f of x, is rising until it reaches the endpoint at 4.4, so it also must be a local maximum. So my local maximum values are at x equals -1 right here, because the derivative changes from positive to negative. And then again here at 1.5, because the derivative changes from positive to negative. And then at this endpoint, because the curve rises to that endpoint, therefore finding a maximum. Now what about minimum values? Minimum values are going to occur at those other points here where the derivative is changing from negative to positive at that critical point. So right here at this critical point, we had negative to positive change. And then at this critical point, we had a negative to positive change. So those two are local minimums at x equals 0 and at x equals 4. By the way, notice we don't know the actual point on the curve. We don't know the value of the value of y on the curve here. We only know where the critical point is and where the x value is. And then we also said that this endpoint, which is a critical point and an endpoint, we noticed that the curve rose after that endpoint. So over here, we'd say f of x started somewhere. Actually, it started at -3.5, -2. So it's actually -3.5, -2 would be down here somewhere. And then the curve was rising. So this value, this endpoint, is actually a local minimum. Part F says in this same interval, by the way, there's a typo here on your worksheet, so you should change it to from -3 to -2. So we're only looking from -3, so from this point right here, to -2, which is right here, from this point to this point. So from -3 to -2 on that interval, where does f, again, the curve we can't see, achieve its maximum value? So we're not looking anywhere else on this curve. We're just looking from -3 to -2. Where is the maximum value of f? Now remember, we're looking at f prime, not f. F prime reaches a maximum right there, but that's not the question. The question says, where does f reach a maximum? Well, if you look at this function, the derivative function from -3 to -2, notice in this interval, the derivative curve is above the x-axis. It has all positive values there, which is telling me that f has positive derivatives from -3 to -2, f has positive derivatives. Therefore, f is increasing over that entire time. So on this small interval from -3 to -2 inclusive, at x equals -2 must be the point where f is reaching its maximum, because this derivative curve is telling me that f is rising from -3 to -2 because the derivative of f of x is positive over this interval. So let's read what we have. F of x has a maximum value on this interval at x equals -2 because on this interval the derivative is always positive. Therefore, f of x must always be increasing, and the maximum would be reached at the end of the interval. All right, that was a tricky question. Let's look at another one. So this is another worksheet that relates the graphs of the original function, the derivative function, and the second derivative function. And again, what is given to us is the graph of the derivative. This worksheet is also in your worksheets folder. It's called Relating the Graphs of f, f prime, and f double prime. All right, so let's answer some questions that they have here. So let's try to see if we can do these same type questions. Now, I'm sorry I didn't label, I should have labeled this. This is -1, -2, -3, -4, -5, -6, and so forth. 1, 2, 3, 4, and then going in this direction. So first question said, what are the critical values of f? Again, we're not looking at f. We're looking at f prime. But the definition of a critical point is when the first derivative is equal to 0 or undefined. So the first derivative is equal to 0 here, 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 and here. So these are all definitely critical points. F of x has critical points whenever the derivative is equal to 0 or does not exist. And since we're looking at the derivative of f, the critical points would occur at -9, at -5, at 8, and at 10. Now, what a lot of students try to give to me is they try to give me this point down here. Now you have to be careful